And now I give the floor to Aikaterini Giannikopoulou from National and Kapodistrian University of Athens. The title of her presentation is Case Studies on Coastal and Marine Geomorphology. Katerina, the floor is yours. Can you share your monitor, please?
Yes, waiting for the connection right now.
Okay, perfect.
Can you see my screen?
Perfect, yes, we can see.
Great. All right. First of all, I would like to thank you for the invitation in this workshop. I will be presenting a few case studies on coastal and marine geomorphology from different areas of Greece, conducted by my colleague Apostoli and myself. The first case study regards the application of the Coastal Vulnerability Index for the coastline of Chios Island. Chios is one of the southernmost islands of the Cycladic archipelago, located in the central part of the Aegean Sea. The area of the island is about 105 square kilometers with a coastline length of 110 kilometers. The island has an elongated shape with direction from northwest to southeast. Regarding the methodology for the study, the Coastal Vulnerability Index is a simple method to estimate the vulnerability to erosion of any coastal area in relation to future sea level rise. It takes into account 6 variables that are divided into 2 groups: geologic variables and physical process variables. The geologic variables are geomorphology, historic shoreline change rate, and coastal slope, and physical process variables include significant wave height, tidal range, and sea level change. Each variable is ranked according to the values of the table you can see here. Data sources used for the present study include topographic maps, satellite images, digitized historical maps, literature research, and fieldwork data. For the post-processing of the data was used the ArcMap software. These are the results for the vulnerability ranking of the geologic variables. In this map and table is depicted the vulnerability ranking for the variable of geomorphology. Here we can see the ranking for coastal slope values, and this is the map and table for the vulnerability ranking of the shoreline erosion and accretion rates. This variable expresses the trend of the coastline position alteration, with positive numbers indicating accretion and negative numbers indicating erosion. Here we can see the results for the vulnerability ranking of physical process variables, namely the relative sea level change, tidal range, and mean wave height. The 6 variables of the area were correlated with the use of CVI in order to express the relative vulnerability of the coast in relation to future sea level rise. In the final map, the red color highlights areas where the various effects of sea level rise may be the greatest, taking into account that physical process variables and shoreline erosion and accretion rates are the same for the whole island. Those that effectively determine the CVI are slope values and geomorphology. Overall, we can see that the vulnerability is unevenly distributed among the 5 risk categories, with low risk prevailing for the most part of the island's coastline. The very high vulnerability ranking characterizes locations of small slopes and sandy pocket beaches. The second case study focuses on the sedimentological and geomorphological features of Milopotas Beach in Chios Island in order to determine seasonal changes in the texture of coastal sediments, and preliminary results are presented. Milopotas Beach has a total length of 702 meters with a direction of northwest to southeast. The upper limit of the beach is bounded by vegetation and human constructions. At the south and central part of the beach, there are 2 torrent estuaries supplying the coastal sediments with fluvial torrential deposits. Fieldwork was conducted in April and September of 2018, including mapping of beach morphology in seasonal scale, including a differential GPS and sediment sampling along the profiles. The method of dry granulometry was conducted using a precision balance, a series of sieves of different diameter, and a vibrating device. Statistical parameters of the granulometry results were calculated using Gradistat software. Samples collected across the cross sections of the first position, the northern one, namely MIL S1 for the spring profile and MIL A1 for the autumn profile, are characterized as slightly gravelly sand, while near the shoreline there is an appearance of sandy gravel in the spring profile and gravelly sand in the autumn profile. The berm zone is more distinct during autumn than spring, as indicated by the measured topography. At the underwater part of the cross-section, spring profile is characterized by steep slope, while the autumn profile by gentle slope. Cross-sections of the second position, this is the central part of the beach, are characterized by alternations of slightly gravelly sand, and sandy gravel sediments. The coarser material probably indicates the fluvial deposits. Topography is characterized by steep slopes in both profiles. Cross-section MIL S3 for the spring profile of the third position is characterized by gradual transition of sediment texture from sandy gravel to sand. Along cross-section MIL A3, the majority of the samples are classified as slightly gravelly sand. Topography is characterized by gentle slope in both profiles. By comparing the cross-sections in seasonal scale, the central and the southern part of Milopotas Beach represent a stable morphological and sedimentological regime. The seasonal cross-sections at the northern part of Milopotas Beach indicate changes at topography, including the berm zone and the slope of the underwater part of the cross-section, while sediment granulometry does not present significant variations between seasons. The next case study focuses on the geomorphological features of Vravrona Beach in order to determine the seasonal changes in shoreline position caused by both natural processes and human activities. Vravrona Beach is located in eastern Attica and has a total length of 300 meters with a direction of north-northeast to south-southwest. At the north part of the beach there is a torrent estuary which supplies the coastline sediments with fluvial torrential deposits. The northern limit of the beach is bounded by vegetation, while from the central part to the southern part there is intense anthropogenic impact. Fieldwork took place during January and September of 2018, including mapping of beach morphology in seasonal scale using a differential GPS and measurements of the shoreline position. The observed changes during fieldwork were quantified using the digital shoreline analysis system in the ArcMap software. Differential GPS measurements of the coastline position for each season indicate changes mainly at the northern and southern part of Vravrona Beach. In detail, regarding the winter profile, at the southern part there is a retreat of the coastline position of about 9 to 5 meters landward in relation to the summer profile. Respectively, the accretion of the coastline at the north part of the beach is about 5 to 8 meters seawards. At the central part, coastlines of each season are approximately at the same position. The overall picture of shoreline displacement indicates the presence of the planation process, reflective of natural seasonal change processes, which seems to be more pronounced at the northern sector of the beach. The final case study regards the structure of Argostoli Gulf. In this work, a multifactorial approach is used, aiming to contribute to the knowledge regarding the modern morphology of the area's seafloor and its shallow structure. Kefalonia is located in the Ionian Sea. The study area consists of two parts of the semi-enclosed Argostoli Gulf of the island. Livadi Bay is situated at the northern part of the Gulf, while Argostoli Bay is located at the southern end. Kefalonia is located close to the northern end of the Hellenic Arc. Due to its current geodynamic status, the island is subjected to regional compression, which in turn creates a series of consequential thrust faults and faults developed parallel to the Hellenic Arc in a northwest-southeast orientation. The elongated Argostoli Gulf is an asymmetrical syncline. In this map are depicted the main faults and thrusts that their position is either identified or estimated by several authors. For the present work, acoustic methods were used to map the seafloor combined with surface sediment analysis. Acoustic data were obtained with the use of a single-beam echo sounder and a chirp side-scan sonar system. Survey lines for updating this data are visible on these maps. Additionally, subbottom profiles were collected from both areas. Again, the survey lines for the sub-bottom profiling are visible on the maps. For the post-processing of all acoustic data, were used the Lorentz Sonar Viewer, ArcGIS, and SonarWiz software. Surface sediment samples, 13 from Argostoli and 20 from Livadi Bay, were collected and analyzed. Collected sediments were subjected to grain size analysis using the method of sieving and laser granulometry. Statistical analysis of all granulometry results was conducted with the Gradistat program, and Folk's classification system was used to determine the texture of each sample. Moving on to the results, this is the bathymetric map of Livadi Bay, and these are the results for the bathymetry of Argostoli Bay, accompanied by the slope map of the same area. Regarding the results of side-scan sonar imagery for Livadi Bay, identified features according to backscatter values are noted on the side-scan mosaic. These images include the textural classification of Livadi samples. Marine sediments are generally more fine-grained than coastal samples. Those located in less than 3 meters depth are mostly well sorted, in contrast with those located in greater depths that are generally poorly sorted. A detail of the mosaic is shown in magnification, demonstrating the difference between high backscatter vegetation coverage and low backscatter fine-grained seafloor sediment. These are the results of the side-scan sonar profiling for Argostoli Bay. Identified features according to backscatter values are noted on the side-scan mosaic. Those images include the textural classification of Argostoli sediment samples. Most deep-situated samples are fine-grained, with only a couple of them classified as some sort of gravel. All the sediments tend to be poorly sorted. Finally, 2 details of the mosaic are shown in magnification. Regarding the acoustic profiles from Livadi Bay, most of them were highly distorted due to the presence of gas within the shallow sediments. The representative profile LV3 is presented here. A high amplitude reflector is noted in green as surface R. On top of it, a main depositional sequence is identified, consisting of parallel horizontal continuous reflectors of medium to high amplitude, noted as U1. In all of the profiles for Argostoli Bay, the major surface identified, surface R1, also corresponds to the acoustic basement of the data. Additionally, a main depositional sequence, U1, is identified. This is the profile AR1. The internal reflectors of the U1 sequence are of medium to low amplitude. They diverge towards the northeast. They continue being parallel to the southwestern side and terminate laterally as they overlap onto the R1 southwestern slope. Surface R1 exhibits an abrupt disruption towards the southwestern part of the profile. The red dashed line accompanying this feature indicates the presence of a fault. Next is presented the profile AR3. It is parallel to the previous one, located at the central part of the bay. Seafloor is mostly horizontal. The reflective surface R1, noted in green color, begins with a steep slope to its southwestern side, continues straight with a slight downwards inclination to the northeast, and it appears to terminate against a very steep surface noted as R1 accent. This feature is thought to be indicative of a fault, noted with a dashed red line. Results of the sediment texture of the samples, in the case of Livadi Bay, were plotted on the bathymetric data in order to reveal any distribution patterns of the surface sediments. Those results, as well as the results from the sample's grain size analysis, were compared to the side-scan imagery of the seafloor. On the side-scan imagery, there are portions of steep slopes and coarse material visible to the east, and a mild local topographic depression along the northwestern coastline. In the deeper part of the bay, a large area of fine-grained sediments is visible. A large zone of marine vegetation meadows is identified at the shallows, followed by a transitional zone featuring sparse vegetation on fine-grained sediment. These results suggest that the depositional environment along the northwestern coastline is affected by typical coastal processes, namely a longshore current with direction from northeast to southwest distributing the sediments, while the inner part of the bay corresponds to lower energy conditions. Regarding Livadi's seafloor structure, acoustic data of the area are heavily obscured due to the presence of gas thought to be of biogenic origin. It was determined that the sequence and R surface identified in this profile are the same as U1 unit and R1 surface identified in Argostoli Bay, respectively. Regarding grain size analysis of Argostoli samples, their textural classification and sorting values are considered to reflect the low energy marine conditions that characterize the bay. On the side scan image of Argostoli seafloor were identified features reflecting the topography of the area, such as zones of steep slopes along the eastern side of the bay. These findings are validated by the bathymetry of the area as well. The rest of the identified features are related to the type of seafloor coverage, including sediments and vegetation. Sediments of the seafloor and local topography are highly disturbed by anthropogenic activities, reflected by the mixed high to low backscatter area along the central portion of the bay. Moving on to remarks of the seafloor structure. The image to the right features the slope map of Argostoli Bay seafloor in relation to the position of the acoustic profiles, as well as the identified or probable major fault positions according to several authors. This is a portion of the profile AR3, including all the main features identified in the area. These are the following. The reflector R1, that is interpreted to be an erosional paleosurface, previously exposed to subaerial conditions. A main sedimentary unit, the U1, that is interpreted to be a Holocene depositional sequence. It presents a maximum thickness of about 20 meters. When the steep slope of the eastern side of the bay is compared to the sub-bottom images of the same position, namely the northeastern end of profiles AR3, AR4, and AR5, it is evident that it extends beneath the seafloor until it meets R1 surface. Divergent reflectors of U1 sequence indicate progressive tilting of its depositional surface during sedimentation of the sequence. The aforementioned evidence indicate the presence of a normal fault acting along the eastern coast of Argostoli Bay, and finally, the western side of Argostoli Bay. Generally, it does not feature any abrupt changes. One such feature is identified at the northwestern end of the acoustic data, interpreted to indicate the presence of a fault. The lateral termination of the U1 unit against R1 does not suggest subsidence of the sedimentation surface. Concluding, sediment texture, sorting, and distribution of the samples correspond to the low energy conditions that characterize both areas. The seafloor of Argostoli presents evidence of disturbance due to human activity. Sub-bottom profiles reveal the main Holocene sedimentary sequence, U1, laying on top of an erosional surface, marking a time boundary for marine transgression in the area. Taking into consideration the eustatic sea level curve, the present-day sea level, and thickness of the U1 seismic unit, it is indicated that both areas' submergence took place after 10,000 years ago. Finally, the anaglyph of Argostoli Bay in combination with morphological features of the R1 surface identified in the sub-bottom profiles indicate the presence of a normal fault along the eastern side of the bay. Argostoli Bay could be characterized as a half-graben sub-basin of the main Argostoli Gulf. Thank you so much for your attention. That is from me.
Thank you so much, Katerina. A very beautiful presentation, a lot of data and results about the Greek coasts. And in addition, you presented a variety of approach to study the coastal sector. So I congratulate you. Are there some questions for Katerina? No? So I have a lot of questions for you. First of all, I would like to ask some question about the last case study in the Agostoli Gulf because it's my cup of tea. I like this kind of service. And the first question is a simple curiosity. What kind of echo sounder did you use for the bathymetric survey? A single beam or a multi-beam?
A single beam. It was
okay.
And
have you created a 3D model of the seafloor by overlaying the side scan sonar and bathymetric data and eventually the subbottom profile data?
Yes.
Yes, and
yes,
it was useful to better interpret the side scan sonar data.
Yes, it was, because it gave a better view of the overall geometry of the findings, because 2D acoustic profiles are a little bit difficult to be correlated, the position of the one in relation to the position of the other. So the 3D representation is really useful in terms to gain a better understanding of the whole space and how each geometry relates to the other.
Yes, of course. And finally, I wonder if you have created an acoustic signature by overlaying the core data with the side scan sonar ones. Have you created typical acoustic signature to create a map of the seafloor?
No, that one I have not done.
Oh, okay. So in the last case, when you show the side scan sonar interpretation, in which way you created the boundary of the different sediment layers?
By comparing the relative comparison of the backscatter backscatter values.
Okay. Thank you.
Oh, you're welcome. Thank you.
Thank you so much. I congratulate you, Hannah.
Thank you so much. Thank you so much.
Because you are presenting very interesting data.
Thank you.